Hello, in this video we're going to use a graphic approach for another second example, and hopefully by the at the end of the first video for the graphic approach you compare the results you had with the analytical approach. You realize they are the same diagrams, right? So if you haven't done so, please do that right now. Check, see if that's the same approach, and hopefully you already kind of conclude which method is easier, right? And I think we probably unanimous, we're all gonna agree that graphic approach is way easier than the analytical approach. Doesn't mean we're not gonna ever use analytical approach. We will. It's method its own. However, graphic approach is probably preferable to getting some answers right away. Okay, so now let's get into today's new example. We're gonna call this low shear bending graphic approach and example 2. So if you remember, what example we had for analytical approach is a simply supported beam. We have a moment right in the middle. And here I don't need to go ahead and solve the reaction support once again. We just take out the results. It's m naught over L, and this is m naught over L. So refer to the previous video to see how we got those two reaction supports. Now, using graphic approach, again, we don't need to do another cut. We don't need to do another FBD or equilibrium equation. We directly jump into our low shear bending. Okay, so the load here, actually I'm going to save some time. I'm just gonna directly using this, right? That's our load. Basically, it's our FBD. I'm gonna highlight this a little bit better. Now, we have our load diagram. The next one is our shear. So be familiar with those rules. Okay, the first rule, remember, if you see a concentrated load, that translates to the shear is going to be the same direction, same magnitude. So that means at the beginning of this point, right at this point, we're going to go downward, m naught L, because it's going downward. So it's going to be going downward and ends right here. Then when you move forward, move along, there's nothing going on, so they stay at the same shear. And however, at this middle point, what do we see? What do we encounter? We encounter this moment. But do we need to do anything? The answer is no, because this is a moment. And here we're working on shear diagram. Okay, so this moment right here does not affect my shear diagram at this point, because I don't have another concentrated load or anything, or distributed load. It's a moment. This moment, however, will impact your moment diagram down here, but we are not there yet. So at this point, we're going to continue to go. So watch out for that point, okay? Once you get here and you have a concentrated load going upward from negative m naught over L, go up exact number, so that's going to get back to 0. That's our shear diagram. Okay, the last is our moment. So far we already learned a very important rule, which means moment is integral of shear. Sorry, wrote this wrong. Moment is our integrate of our shear. So in other words, one of the rule we had it before, rule number 4, area under the shear is going to be our bending moment, right? So we are going to calculate the area underneath this shear curve. What's the value for that? It's a rectangle. The area, it's below. If it's below, that means it is negative value. And this rectangle has a length of L, height, negative, M naught over L. Again, I don't care about this negative value because that's just going to be the height. I already take care of this sign because it's below. That will give us negative M naught. So what does that mean? It means if I'm going to start moment here, if I'm going to integrate this whole thing, I'm going to have to minus value because it's below until I'm going to minus M0 at this last point when we integrate this entire area. Okay, but now let's start from beginning, which is right here. When you integrate shear, it starts at 0 because the area underneath this line, it's 0. So, and until you get into the midpoint, why do we stop at the midpoint? Because we have this moment that's going to impact this moment diagram. So when we look at just the first half where the green goes, that area is going to be half of this value, right? Negative M naught over 2. And so we start at 0 when you integrate, and you're going to integrate, which means we're going to add this area. This area is negative value, add this negative M naught over 2, getting to this point. And how do we connect to those two dots? Linear line. We talk about if this is a straight line, which means y is equal to a constant, then when you integrate it, that will give us a power of 1. So that's a linear line. Now, we stop in the middle because there is a concentrated load here. Now let's go back to our rule. See which one has about the concentrated moment, which is our rule number 6. If this is clockwise rotation, it's going to jump upward. Okay? So this one, moment, happened to be clockwise rotation. So which means we're going to jump upward from this negative M0 over 2. Jump upward how much? This exact value of this moment. So we're going to jump plus M. That land us to M naught over 2. Then, after that, we're going to go back to our shear diagram to continue to integrate this second half. The second half of the area will giving us negative M naught over 2. So we start at M naught over 2, and we're going to integrate this negative area. So at this point, when you add all those negative area together, you're going to add this much value on the top of that value. That will give us 0. Because how we get this is M naught over 2 from this plus this negative area. That gave us 0. Again, this will be a linear line because this is a constant, right? When you integrate a constant, you get power of 1. Okay, so that's going to be our moment diagram for this problem. Just to be curious, we can go back to look at our analytical approach, see if we get the same graph. So let's see. Exactly the same graph as you can see here, right? So that's our graphic approach for this particular problem. All right. That concludes our video this time. See you next time.